Welcome to Complexity Made Simple. My name is Paul Allen, and in this video newsletter, what we're going to take a look at is a very simple case study which makes the point about looking at your problem from the point of view of, do you have a problem with chaos or do you have a problem with control? So it goes like this. We're going to go chaos or control. It's the fundamental question you need to answer at the beginning of your project. So you're going to see this in the case study. And what I mean by this is, does your problem look like this? Too much variability? Or does your problem look like this? Your process has moved off center and you just need to adjust the aim. This will take you 3 months to fix. This will take you 3 days to fix. We're going to have a look at a case study and you'll see the whole thing come alive. It's a problem that looks like this, but the first thing they have to do is visualize that element of the problem. Let's go to the case study. Okay, so here we go again with another case study, and just like the first case study, this is a study which is all about a single event, a root cause, and it shows simple use of diagrams in order to find the root cause or to find the fact that it is a root cause, and how simple that is. But it also shows the difference between chaos, control, and excellence. This is a process that was in control. Something's gone wrong. When that happens, it's usually a single event. So it's all about first time pass rate for this particular product. Here it is. Let's show you the product. It's essentially a sensor that fits on an aeroplane wing, and it tells you where the aileron is sitting. It tells you where the flap is sitting on the wing. And essentially, this rod moves up and down inside a coil, and the coil therefore can sense where the end of the rod is. That's the product. Here's the product which is sitting on the test jig, and what the test jig is doing is moving the part a known distance and then making sure that the zero position is correct. So it's looking for a particular zero position, and that's what the product has got to do once it's assembled. So very, very straightforward. The current yield, however, look, has gone to 44% when it used to be 100%. No problem at all. You're going to see that in the run chart in a second. You can see that currently, if that continues over the year, it's going to cost the company almost $164,000. So very expensive, even though the units are. It's quite low number of units, but very expensive product to make scrap with. And here's the current performance graph. This is just discrete data, pass, fail. Here's how the batches have been performing. Here we go, look. Everything in control. It's a process in control. There is no chaos going on here. And then all of a sudden, what the hell was that? What's gone on here? So this is the case that when you look at graphs, you're looking to say, is my problem chaos? Is my problem control? Or do I want to go to excellence? Not sure I've spelt that right, but still. Or do you want to go to excellence? And if you know whether you're in chaos, control, or excellence, typically if you're in control, this problem is going to take 3 days, 3 minutes, 3 weeks, maybe to fix. It's going to be short term. If you're in chaos, 3 months. Minimum 3 months. You have to know what type of problem you have before you start. Here is another great example. We are in control. Something's happened. What is it? Now this happens to be measurable data in terms of what we're doing. This null position is measurable. The jig that you saw earlier measures the null position. So we can take, in this case, 25 units, and we can look at the first time pass data. Now we have it, lovely normal distribution. So in that sense, it's in control in the sense of we're getting a normal distribution, which is always good to see. It's not too chaotic. But if we look at that as a capability diagram, oh, okay, we're off center. This is one of the reasons why when you look at this, it's normally very easy to move processes on the mean. If you're trying to shift the mean, which I'm going to call the signal, that's usually very easy to do. There's dials, settings, tolerances, nominal positions that are very easy to move around and to change the signal. If what you're trying to do, on the other hand, is affect the noise, if you've got a capability problem that looks like this, for example, and the defects are sticking out both sides, so it isn't about moving the signal, that is about squeezing the noise. If you are trying to squeeze the noise, that's going to take 3 months. This is going to take 3 days. Maybe 3 minutes if it's a dial on a machine. So there are the diagrams telling you, what's my problem? How difficult is it to fix? What have I got to do next? And this is what these diagrams are about. We call this, obviously my training is called Six Sigma. This isn't Six Sigma. This has been around for 60, 70, 80 years. This is just good process analysis. So now we know we're trying to shift the mean. We've got to find out what's done this, because this has clearly been sitting happily inside those tolerances for a long time, and suddenly something's changed. What is it? So okay, we're going to look at the process flow for the process. We've also got to look at the variables for the product. So this isn't just about the way we're assembling it, although that could be an issue. It could be tolerances. Something's wrong with the tolerance. So this is about the parts as well as the process. There's the process flow. There's a more detailed process flow. So we've got winding, we've got assembly, we've got making electrical connections, and we've got the test at the end. Yeah, so we got a little bit more detail there to help us. And then we go in and looking at the wire assembly method and the process, the case assembly as well. Then we start looking at the variables. Are the variables under control? Well, if you look, lots of C's here, so that's telling us that actually process is well controlled. Do we have a standard operating procedure? Are we happy with that standard operating procedure? Is it clear and unambiguous? And do we use it? The answer here is yeah. What else we got? Tube winding. Again, look, all C's. Yeah, the whole thing. Happy. Process is in control. All good. Then one of the things we've done is taken a look at the tolerance stack up. So what does the design create? Should the design create that off-center distribution that we saw earlier? If we stack all the tolerances up, what actually should happen? Well, here is a Monte Carlo simulation. So this is a calculation. It's a prediction. Okay, it's a prediction of how the tolerances should act and react. What distribution will they create? Clearly not the distribution we saw earlier. Slightly off center, but actually the other side of the center, whereas we were seeing the actual result all over here. So the design the tolerance stack-ups should work. So the tolerances are right. Okay, let's keep going. So case assembly. There's something identified there. So all the parts are okay. Lots of C's, size of the parts, etc. So everything's to tolerance. The tolerances should work, etc., etc. But we do have this little question mark here. Parts have been changed recently. Keep it moving. So, in what way were the parts changed recently? Well, the changes relate actually not to the internal assembly of the item, but to an external face. So this was changed recently. So these external tolerances, these two things here, were both modified recently. And in theory, these shouldn't be having an effect on that tolerance. They were outside and not part of the tolerance stack up at all. This is the machining operation. So it is the machining of those faces there. However, it turns out those faces are the datum face for the jig that we saw earlier. So when the part is placed in the jig and then we try and measure the datum of the shaft that's running through the center, this is the datum face right here. And what we've done is moved the datum face because of some other requirement. A requirement obviously to do with the way the part performs or the way the part fits in its position on the plane. It's been modified without giving it a thought of the fact that it happens to be a datum face for the jig, and what they've done is kicked that distribution all over to the left that you saw earlier in the CPK diagram. So we had the CPK diagram. The result was sitting sort of like that. And that was all to do with that single change right there. Now, of course, this is a great example if you wanted to go and do, and they haven't done this, but if you wanted to go and do the famous 5 whys, asking why 5 times. Why did the parts fail? Because the tolerance was changed. Why was the tolerance changed, etc., etc. If you want to do the 5 whys analysis to get to the real root cause, why did we not know that that face had another customer associated with it other than just the final customer? That would be a great thing to do. It's not something that they've done in this case study. They found the problem, they fixed the jig, they've centered that distribution. As I said, how long did it take them? 3 days. That's all it took them. Using the right tools, knowing what's going on, taking the right action. That's what these tools are about. Are you in chaos? Are you in control? Or do you want excellence? Once you know what to do next, and you know how long the problem will take to fix and what you've got to do to fix it.
Okay. Now, you could see that was a relatively involved analysis, but once we discovered the problem, the solution is relatively easy to implement. But this question, so when you talk about defining your problem, to me, that's what defining the problem means. Do I have this element of physics or do I have this element of physics? Because once I know what the physics of the problem is, I know how to fix it, and I'll know whether it's going to take me 3 days or 3 months. By the way, not only that, this takes a team. Usually this can be done by one person. So these two techniques, you can use your 5 whys here. This is where 5 whys comes in. 5 whys up here, useless. Okay, so understand whether you've got a chaos problem or a control problem understand what work you need to put in, and there's all sorts of other things you will understand, what tools to use, what's going to fix your problem, etc., etc. In this case, our case study was just move the aim. Takes us 3 days, and then we can start to make more money.